Hi! Today we're going to be talking about rotational inertia with the help of this Jedi artifact. Okay, so rotational inertia is basically a representation of how much force is required to move something affixed to a specific axis. Hi, Jethro! Yeah, so basically, well, if you look at this equation that tells you the rotational inertia, it's basically just mass times the radius squared. This is only for objects that are, well, like this. So like pendulums, all the mass is away from whatever axis it's spinning on. So yeah, that's the equation for that specifically. It doesn't apply to like a bow staff or anything. But if you look at it, it's mass times radius squared. So that means that the larger the radius, the higher the rotational inertia. And it actually makes more sense to me as moment of inertia because it's the moment, it's the amount of force you have to use to get it started. I'm guessing that these would be specifically like the amount of force that you need for it to go one revolution around. Oh, I should tell you what this is. This is a poi. It's basically a type of pendulums that are used in circus arts, flow arts, stuff like that. This one is glowy glowy, which I love. And basically, a poi is something where it's one piece of string this long. You usually have two of these, one in each hand, and that's how you're spinning, right? Well, this is a rope dart. Well, a poi attached to a length of rope, thus transforming it into a rope dart. It originated as a type of weapon, which is pretty rad. But this has been something I've been like practicing playing with. I decided to do, the sciencey aspect of like, well, I understand what rotational / moment of inertia is, and I do this already, so I might as well just kind of see what the math is. So the way I did that was by measuring placement between knots. So I know the lengths that I'm going to. So basically with a rope dart, instead of staying at a fixed length, you can shoot it out and go to a different knot. Right? It's really fun. Have to take this away, change the mood. Ooh. Love that. Colored lighting for physics videos. ContraPoints would be proud. So the first knot has a total length of 27 centimeters. Next is 60, 87, and 118 centimeters. And then this one is 183, but this is basically what gets wrapped around my hand when I'm doing my thing. So I don't actually know how much this thing weighs. This part is hollow, but this part is actually pretty heavy. I'm gonna assume it's about a pound. And because we're doing science here, we're using metric, so I had to convert it to, goodness me, where is it? Kilograms. If we assume this thing is a pound, convert it to kilograms, that's 0.5 kilograms or 4.5 grams. So I just made this little equation. Because I'm going by knot length, I had K knot as my radius variable, variable, and the rotational inertia as I, and plugged in all those numbers. And as you can see, the longer the length of the radius, the more energy needed to get it moving. So that means that something this long would take a lot of force to get it swinging, and something as short as 27 centimeters can get it going really easily. Like, that same amount of force would do like twice as much. Yeah, and that has to do with something called conservation of motion. Okay, so if you have something that's already swinging at, say, this length, and you shorten it, you bring it closer to the point of origin or axis, that would change the ratio of energy to movement. So you would have a lot of force going into something very small, which would make it go really fast. So you can use basically this equation to kind of understand the movements of what I'm going to be doing.